Hey everybody, in today's video I'm going to talk about what an integral is and specifically give you the intuition for the idea and the notation and all the formula and everything like that. So the integral is basically our generalization of area, and it's used commonly when we have functions and we're trying to take the area under the curve, which in this case I called it f, between two endpoints. And I'll just say we have between x equals a and x equals b here, okay? And we're trying to find this area, and obviously we can't use any geometry formulas, any this is exactly equal to a trapezoid or anything like that. Sometimes we get lucky and we have pretty straight lines or circular looking shapes, but in this case we have a weird function that has this weird behavior and it's not straight. We can't really do much with this. So we have to come up with a new formula to figure out for any general function that is nice enough that we can find its area between two endpoints. And this is kind of a hard task, right? How would you go about doing this? Well, if you saw my previous set of videos on a similar topic about what is a derivative, I started with an approximation, and then I, made it more exact through some limits and stuff like that, which again, we will be using limits in this video, until we actually get the exact answer. So by doing something, we eventually get closer to the real answer. So we'll talk about what that something is in this video. So first of all, let's try to figure out how would we go about approximating this weird function here. Because we can approximate it. Right now we can definitely approximate it in a few different ways. We could maybe consider the midpoint of this interval and then just draw like a line here. So if the midpoint is somewhere like here, right, then we can just kind of draw up to the function and then do something like this. And then, that's an approximation, so then we would just, find the area under that rectangle. We could approximate it in a few different ways. We could look at trapezoids, rectangles. I'm just going to be focusing on rectangles in this video, and the two methods that I'm going to be focused on are the endpoint methods. So we can think of two different ways. We can think of something like this. We can make a rectangle based on this left endpoint. And we can, draw a dotted line and figure out the area under this, rectangle here. So the area here, and I'll just call this area left, is going to be equal to b minus a multiplied by f of a. And then we can also do the area for the right-hand endpoint. Well, that's just going to be a little bit higher up here. Right, and it's going to be a little bit bigger. So again, this is going to be b minus a times f of b. And the b minus a just comes from this distance here. And so, we have these approximations. These are both approximations, but they're not quite exact, right? For the purposes of this video, I'm going to focus on the left endpoint in every example I do. It's just arbitrary choice. It's because I just want to be consistent throughout the video. So it doesn't really make a difference because they're both very similar in the way they're constructed anyway. So it's not that big of a deal. So I'm just going to choose to work with the left endpoint every time. So we have this approximation, which both of them were larger than the actual area. We can see the areas here, but we had our approximations like up here, it would be the whole rectangle. They were too big. Sometimes you might have under approximations, or they might be pretty close, but in general, this is not a great approximation. Well, what if we split this interval up into two subintervals, right? What if we just draw a line here about halfway through, and then, we had this left endpoint, and then this left endpoint, and now we have an over approximation here, and an under approximation here, so that's a little bit of a closer approximation in general. Still, it's not great. We want to have an approximation that stays pretty close to the function, which you can see here and here it deviates quite a bit. So it's not that great, but we are getting a little bit better. What if we just, make more subintervals? And this seems to be the way we are approximating it and taking that approximation so it's a little more exact. We're just going to keep dividing into more and more subintervals, and I'll just do a few more here. Let me make this a little better here. So then we'll do like 16, and I'm not going to worry too much about making them exactly the same, but just understand that they're supposed to be of equal width, basically. So now we have supposedly 16 subintervals, and we can take the left-hand approximation of each one. So I'll just draw a few. So here we take the left-hand input, and you can see this first rectangle is an over approximation. So is the second rectangle, and the third, and so on. But then if we go to the other side over here, the left-hand approximation goes up to there, and here it goes up to here. So these are under approximations. And you can, imagine how this goes. Down here in the middle, we have, pretty close approximations. So you can see some are over, some are under, some are pretty close. But what we're going to do is we're going to sum up all of them. And that should be a lot more precise. So here's what we did. We took the number, we took basically the width, So here's basically what's going on. We're going to find the area, currently it's still an approximation, but it should be a pretty good approximation. We're going to do that by taking the area of each rectangle and multiplying it by the number of rectangles. And so what we can do basically is figure out what the area of each rectangle is going to be. And so this is going to be a sum. And so I'll say this is going to be a sum. And it's going to be from I equals 1 to n, okay? And that n is the number of rectangles we have, and we'll talk about what happens to that n as we go on. Right now n is 16, but I'm just going to do this a little more generally, okay? And so what we're going to do is first we're going to take the area of each rectangle. So remember when I did that earlier, it was just b minus a times f of a, right? So what that was the width of each subinterval, and when it was just that one interval, it was just b minus a. But here, the width is going to be smaller. It's going to be b minus a divided by n, because there are n subintervals there. So it's going to be b minus a over n. So b minus a divided by n. And then we're going to multiply it by the height of the function at that, in this case, it would be the left endpoint. And by the way, if we're doing the left endpoint, it should be I equals 0 all the way to n minus 1. Typically, the right endpoint, it goes from 1 to n, right? So this is like 0, 1, 2, 3, 4, all the way, and then it would be 15 and 16. So the reason why we stop at n minus 1 is because this is that left endpoint over here. This is 16, and then this is 15. So we're stopping at this endpoint, right? So that's why we stop at n minus 1. So just a little convention there. And so then we take the height of the function, so it's going to be f of, well, what? This is a little harder to construct, but we can get there. Let's say we want to take, and I'll highlight it in red. Let's say we want to take, I don't know, this interval here, right? So if we're trying to do that one, and I didn't really draw that well, whatever. If we want to do that one, how would we get the function, the approximation of the function at that? So it would be f of whatever that is. I'll just call that x, whatever. So the way we would do that is we would first count how many rectangles we have, and then that's, so we have 1, 2, 3, 4. We have 4 rectangles before that, so that's 4 subintervals. And then what we do is we take f of that, right? So what we're doing is we're starting at A, and then we're adding on 4 of these subintervals. and that's just going to be b minus a over n times 4. And 4 in this case would be I, so times I in general. So let me recap what I did there. So I started at A, and then I added on 4 subintervals. So here's one subinterval, and then I in this case would be 4, because that's just how many we added on. So this would be 1, 2, 3, 4, and that's it. So this is what we have, and it's kind of complicated, right? So what we often have is this is abbreviated to, this is delta x sub I. Hold on. And then the last step is we multiply by the number of rectangles, right? So this this tells us the width of each rectangle multiplied by the height, and then so that's just one rectangle, and then we multiply by n to tell us, this is how many rectangles we have. And so you can notice that this n and this n will cancel out, and I'll just write this way. So we have the I equals 0 to n minus 1, the sum of those. And I'll start with the f here. So we have f of a plus b minus a over n, and that's all multiplied by I. And then times, well, the n's cancel out here, so we have b minus a. Okay? And so what we can do here is just write a little bit of shorthand, just so it's a little less clunky. This is often just called x star sub I, and then this is often just called delta x or delta x sub I or whatever. I'm just going to call it delta x. And so what we have here is simply, if we want to just be if we want to use this notation, we have f of x sub I star times delta x. And this makes a little bit more sense what's going on. Basically, f evaluated at x star sub I, so that endpoint there, multiplied by the difference, b minus a here. So this is a lot more concise. This is the precise definition, but this is a little bit better to understand, basically. Where, it's just x star sub I, it's just that endpoint, and then delta x is this interval. Okay, so this is the approximation. What if we want to make it exact? So what we do is we make the number of subintervals go to infinity. If we have an infinite number of subintervals, then the widths of these are going to be so close that they're almost 0. Not exactly 0, because, we're never actually going to reach infinity with the number of subintervals or rectangles. But we're going to get, the width of each rectangle is going to be so close to 0 that, we have a really, really good approximation. And eventually that turns exact. So what we can do is say that the limit as n goes to infinity of our sum, I equals 0 to n minus 1, of everything I just said, so x star sub I multiplied by delta x, this is equal to the area, which I will call the integral, so this is our notation, so the integral from a to b of f of x dx. Okay, so let me explain this. So f of x basically is our function being integrated. The dx is pretty much a small version of delta x. So dx is just that width of each subinterval, and that's pretty much what it represents. It represents a little more in general, but this is all we need to know for now. And this is the definition of the integral. So yeah, so this is where that comes from. And you can see you can break this down a little more and just substitute these things in if you want to be totally exact. Or you can just say, x star sub I is equal to that, and delta x is b minus a, whatever you want to do. But this is the definition of the integral. And the way we do computations, there are a lot of different integration techniques. I've made videos with other techniques like that, but there's certainly a lot of videos on YouTube on how to actually compute these things. One important thing to note is that it's the inverse of the derivative. So if you have the derivative of a function is equal to some other function, then if you integrate, you'll get that back, right? You'll get the original function back. So a little interesting thing there. But yeah, this is the definition of the integral, and I hope I made some intuitive sense of where everything comes from. But yeah, that's the end of the video. I hope you enjoyed. Thank you so much for watching, and I'll see you in the next one. Bye, guys.